Our project is response of reinforced sandwich panel walls subjected to lateral loading. The project was done by Kumarappan, Rajkumar, Ponvalavan and Jagadan Prakash, and we were guided by Professor A. N. Kandasamy Sir, Department of Civil Engineering, Veltech. The main aim of the project is to reduce the self weight of the wall, to use the sandwich panels as load bearing walls, to compare the response of sandwich panels and solid panel under lateral loading. The objective of our project is the casting of specimens at proper mix design and structural design, application of proper loading, analyzing the test results in context of lateral loading, cracking patterns, mode of failure and critical load. These are the need for research. To overcome these forces, solid brick walls, solid walls, RCC walls are used. The dead weight of the above walls is sharing most of the load transfer to the foundation. Experimental studies on precast sandwich panels under axial loading, performance assessment of low rise and other following researches were made. Methodology. First we did the selection of balance section, next the mix design, next the casting and testing of specimens, and then finally we did the analysis. We used the code books to find the balance section using XU and XM. Next we go to the mix design. The mix proportions, we did it in the normal way, and we found the mix ratio as 1:2.15 is to 2.18. The specimens, the following are the specimens. First one is the sandwich panel type 1, next one is the sandwich panel type 2 with the following specific peculiarities. Then we come to the concrete details of the sandwich panel, and then sandwich panel infill wall reinforcement details, and then sandwich panel wall load bearing wall acting as load bearing walls with the concrete details. Then the sandwich panel wall load bearing walls and with the reinforcement details. Then the tests to be conducted are lateral load test on wall specimen, compressive strength test on cube specimen, and then finally the split tendons test. The experimental setup for lateral load test, this diagram represents the experimental setup, and then this is the calibration of the proving ring we tested, and then for compressive strength and split tendons strength we use the compressive testing machine and 3-bone hammer. Okay, then we go to the casting of specimens. First one is the sandwich panel type 1. These are the mold preparations, and then placement of reinforcement, and then preparation of insulated materials, and then this is the process of preparation of the mix design, and then pouring of concrete first layer. Next one is the placing of insulated layers, and then reinforcement over the insulated layers, and then finally pouring of concrete for the second layer. Then we did the finishing process, and this is the sandwich panel type 2. Same way as sandwich panel type 1 we did it. Okay, then we went for the curing process. These are the wall specimens. Then casting of cubes and cylinders. These are the pictures showing the casting of cubes and cylinders, and then we cured in the same way. And then go to the testing of specimens. These are the sandwich panels testing. This is the 3-bone hammer test, and then this is the compressive strength test, and then split tensile test. Then these are the crack patterns which we observed. For the portal frame, the initial crack was at 2 kN, and then the crack at left joint, and this is the crack right joint, and then the development of the cracks, and then finally the left corner, right corner, left corner, right corner. And then for the solid wall, the initial crack was at 18 kN, and these were the development of cracks, and then this is the final crack and failure. And then this is sandwich panel type 1, 200 mm spacing, initial crack is at 12.9 kN, which you could see in the diagram, and then there was a 150 mm spacing crack. And then this is for the sandwich panel type 2. This is for 200. There was a 200 mm spacing initial crack at 9.9 kN, and then 150 mm spacing initial crack at 12 kN. And then the compressive strength and split tensile strength. These are the values which we got. These are this one. And then we did the analysis of the test results. These are the pictures showing about the test results. Then the maximum crack. We show the maximum crack with the failure. The portal frame structure fails at load of 6.75 kN, and the width of the crack is at 19 mm. And this is the graph showing the deflection of portal frame. And then this is the mechanism of solid wall. And then this is the crack at fixity. And then this deflection of solid wall in the form of a graph. And then sandwich panel 1, type 2. These are the result analysis of the test results. This is the deflection of type 1 sandwich panel, 150 meter spacing in a graph type. And then this is for type 2. The maximum crack width was at 8.4 mm, and then for the type 2 it was at 8 mm. And then this is the graph showing the deflection of type 2 sandwich panel, 150 mm spacing. And this is a graph showing the deflection and load of type 2 sandwich panel, 200 mm spacing. And we went for the comparison. By comparing, we drew these graphs, and then comparison of the critical load. This graph represents the load and the specimens, and then the estimation of weight and cost. Estimation of this graph, this tableau column shows the estimation of total weight of the specimens, and then this is the total cost of the specimens, and then comparison of weight, cost and failure loads of all specimens. This graph entirely shows the result, shows our result in corresponding to the weight, cost, load for all the 6 specimens. Okay, and then this is the weight of the portal frame is 61% less, the cost of portal frame is 53% less, but it isn't strong enough for the purpose. And then we went for the weight of type 1 sandwich panel is 25% less, and then the solid wall is the cost is 15% less than the solid wall, and it can take 84% of the lateral load taken by the solid wall. Conclusion. We conclude that the results of an experiment combined on solid wall and sandwich panels have been presented, and then the experimental result shows that the weight and the cost of sandwich panels are lesser than the precast solid walls, but it can take up to 70 to 80% of lateral load which is taken by the solid wall. And then type 2 sandwich panel box type can take 70% of the lateral load, and type 1 sandwich panel can take 84% of the lateral load. And then many researches were done on axial and eccentric load bearing capacity of the sandwich panel. They conclude that the sandwich panel can take axial load as the normal precast wall panels. The experimental result of the study shows the capability of sandwich panel to transfer the lateral loads. Hence, we can use the sandwich panel as load bearing walls instead of heavy weight solid walls. In particular, the box type sandwich panel can be used because it is more economical sandwich panel. At the same time, it can transfer 70% of the lateral load taken by the solid wall. Okay, and then these panels have long life, most economical, and can have good aesthetic appearance. When speed, economy, less weight, load bearing capacity and appearance are important, precast box type sandwich panel are the solution of choice. Thank you.